Hello students, welcome to the amazing platform of Physics Wallah. Welcome to the PW English channel, my dear students. We have reached on the lecture 5 of solid state. Till now, we have discussed a lot about crystal systems, my dear students. We have discussed about basically crystalline systems, that what is a unit cell, how a crystalline solid is made since it is a ordered arrangement, right? Yeah. Then we started discussing about a unit cell. Now we actually found out that a crystalline solid can be present in any crystal system. We took the cubic crystal system and then we found different types of arrangement, and then we calculated the rank, the coordination number, and also we calculated the packing fractions. Okay, so these all are the things that we have discussed till now. What are we going to discuss today? So now, my dear students, I have told you what exactly happens when your atoms are arranged. Okay, yes, we have found the packing fraction as well. We also calculated the void fraction, right? What is a void? The void is when a lot of atoms do arrange together, there is some empty space, and that empty space is actually known as your void, right? Yeah. Now these void can be of different types. So now, my dear students, we'll be understanding these different types of voids, how these voids are classified, where these voids can be present, where they cannot be present. We'll be understanding everything about it because it is equally important. I hope all of you are excited. Let's start this session. Just a second, let me see whether the recording is taking place or not. Yes, the recording is taking place, and now we can start. What are we going to discuss today? Before starting this, I told you that I'll make you explain how a unit system is made. I hope all of you remember when we talked about a unit cell, what we did. We thought that in a unit cell, ma'am, you always drew atoms something like this on the corners, right? Yes. And you never joined them. Then why do you say that these atoms actually touch each other? How actual unit cell appears to be? I'll be showing you that, my dear students. So first, let's have some look here. Okay, so now you can see here, my dear students, that this is how a unit cell we draw. Okay, these all atoms are actually present like this, but in reality these atoms are bigger in size and they actually touch each other. Okay, they actually touch each other. So now we'll have to wait till they'll touch each other. Just see, this is how a primitive unit cell looks like. See, simple cubic or primitive unit cell looks like this, and the actual atoms are present like this. Now can you see this empty space between them? Yes, this is actually your void. And if you see along the edge in a simple cubic, your atoms do touch each other. And just see here, my dear students, in a simple cubic along the edges, they do touch each other, right? Yes. And this is how your unit cell actually looks like. If we see, only 1/8 part of the atom is present in one unit cell, right? Yes. So we can just see how 1/8 part of the unit cell is actually present in the unit cell. So this is how a real unit cell looks like, but we have to understand it, so we have to draw it in a very elaborate manner. Okay, yes, I hope you're clear with this, my dear students, right? Yes, perfect. Yes, it's clear. Perfect, my dear students. Now let's move forward. Now I'll show you the next unit cell. Yeah, next unit cell. So now, my dear students, you will understand how a face-centered unit cell works. Okay, so let me just play it. Yeah, so now you will see face-centered unit cell. I told you that along the corners atoms are present, and also along the face center atoms are present. See, face center, this is face center, this is face center, all the face center atoms are present. Okay, now just see, this is how a face looks like. You have a ball, that is your atom, half is in that room and the half is in here room. Now I told you that in FCC atoms do not touch each other. I told you that in FCC atoms do not touch each other along the edges. See, they don't touch each other along the edges, but they do touch each other along the face diagonal. So this is your face diagonal, and actually they are touching each other. So now I hope you're getting the idea why I told you that atoms in a FCC do not touch along the edge like in the simple cubic. They do touch each other, but they'll touch each other along the face diagonal. Okay, perfect. Now I'll just play it. Yeah, it's played. Now just see, and now you can make a diagonal and you can just find out the relation between r and the edge length. Yes, this is how your FCC looks like. Okay, now it will just cut it off. This is how your actual FCC unit cell looks like, because only half of the portion is present in this unit cell, half of the face is present in that unit cell, and along the corners it is exactly 1/8 of the atom present, right? Yeah. So this is how you can see the diagonal here. This is how a FCC looks like. The same way, my dear students, if you can imagine your BCC unit cell, you can also imagine how it actually touches along the diagonal, body diagonal, right? Yes, I hope you're clear with this. Perfect, my dear students. Now we can move forward. We have understood everything. So now, I hope I have given you a better idea of a unit cell, a better idea of how the atoms do touch each other. Now, my dear students, we need to have a better clear picture of the tetrahedral voids. Okay, I'll definitely show you the tetrahedral voids as well, but in the next class. In this class, you'll have to understand, imagine yourself. In the next class, I'll make you see the videos as well. Okay, so now let's start. So if we talk about voids, voids are majorly, the voids which we will be discussing are majorly classified as two types. They are majorly classified at two types. One is your octahedral void, and the other is known as your tetrahedral void. So these are the two types of voids, those are present. Now voids are vacant spaces enclosed by atoms maintaining a definite geometry. I hope you're clear with that. Now we'll be discussing in detail these two particular types of voids. Okay, yes. So you can pause the video, write it down, and then we'll move forward. Okay. So now, one by one, we'll be discussing about all the types of voids. So the first type of void that we will be discussing is your octahedral void. Now, what exactly is a octahedral void? Okay. So now, my dear students, it says that it is a vacant space octahedrally surrounded by the atoms. Now, how octahedrally surrounded? So now, my dear students, you need to understand here that your octahedral void, octahedrally means that it is surrounded by 6 atoms. A void which is formed by 6 atoms is actually known as your octahedral void. Okay. It does not exist in primitive and BCC lattice. My dear students, your primitive and BCC lattices do not have tetrahedral or octahedral voids. They do not have tetrahedral or octahedral void. Your FCC and HCP, your FCC and HCP, this is also known as CCP. These arrangements are close packing. They are called as close packing, and they have your tetrahedral voids and octahedral voids. But your primitive and BCC arrangements do not have the tetrahedral or octahedral voids. Mark this. A question is generally asked from this part because this is something to remember. So you can say that this point is important for you. Okay. It is only present in FCC and HCP. Okay. Yes. Perfect. So please write it down. Then we'll move forward. Okay, so now my dear students, let's try to understand what a octahedral void would look like. I told you that octahedral void is a void which is made up of 6 atoms. Now atoms are solid spheres, we considered it initially. So what actually a octahedral sphere void looks like, you have this, something like this. Okay, you have 4 atoms present. Okay, and your one atom is above and one atom is below. This is something how a octahedral void looks like. Okay, like 4 atoms together and then one atom above and one atom below. Now a space between these is known as a octahedral void. Now try to imagine it. You have one solid ball, sphere ball here, then you put four balls above it, okay, and then you put one more ball above it. Now the space in between is actually known as your octahedral void, okay. Now if we enlarge it, I told you that atoms actually touch each other and only then your void would be formed. So in reality what actually happens is you have something like this, balls present, you have four balls here, and now you have to imagine that you have one ball below, okay. So let me say the one ball below is like this, and then you have one ball above like this. So this is how your octahedral void looks like. So this is your octahedral void. This is known as your octahedral void, okay. Yes, so you have four balls present in the same plane, then you have one ball below it, one ball above it. The space in between is known as your octahedral void, okay. I hope you're clear with the octahedral void. Perfect. Now my dear students, you can also imagine a octahedral void in a different way. What different way? Let's say you have something like this, okay. You have atoms like this. Let me make it a little bit more perfectly. You have something like this, okay. So now what happens is you, just a second, because I have to make you understand, so I'll have to make it beautifully, right? Okay, so this is how you have atoms present. Now what are you going to do? Touch these two, like these three together and these three together, and let's say you are watching this void from here. This is your eye. So what you will actually see is that you will see one triangle this way, and then you will see one triangle this way, one pointing above, one pointing below. This is also a octahedral void. These are the two different types of octahedral voids that can be present in your unit cell. Okay, yes, I hope you're clear with this, how to visualize a octahedral void, a void which is formed by 6 different atoms. Okay, perfect. I hope you're clear with this. Please draw these and then we'll move forward. Okay, I hope you've drawn it. Now let's move forward. Okay, I was feeling a little bit cold, so I just wore the jacket. Now let's study a little bit about the octahedral voids. Okay, it says that the midpoints of the edges and the body center of the FCC are positions of octahedral void. So now we need to understand what are the positions of octahedral void. So it says that, let's say you have a FCC lattice here. So your octahedral void will be present in the body center here. Let's say this is your body center. So one of your octahedral void will be present here, and it says that the other octahedral voids would be present on the edge centers, of all your, this is the edge center, yeah, this is the edge center, this is the edge center, edge center, edge center, edge center, and edge center. Okay, so this is how your octahedral voids actually look. Okay, so the midpoints of the edges and the body center of the FCC are the positions of your octahedral voids. Okay, so now we need to understand why these are the positions where your octahedral voids are present, and it says that in FCC, because we have studied FCC till now, we've not studied HCP, so I'll make you understand everything with the FCC structure. Okay, this is a FCC structure. Let me tell you, I haven't drawn the atoms here, but this is a FCC structure. Okay, so atoms would be present on the faces as well. Okay, perfect. So this is how your FCC looks like. Now I'll make you understand how your octahedral void is present on the edges, in the middle edges, in the mid of the edges, and also the body center. Okay, so now let's try to understand it. The midpoints of the edge is octahedrali surrounded by 4 face centered. Okay, this is something, this is drawn here, and this is the body center. I'll first make you understand the body center, and then I'll make you understand the edges one. Okay, so now my dear students, what you actually have to imagine is, imagine you have one face center atom here, you have one face center atom here, you have one face center atom here, one here. I am not drawing the corner atoms because I want to make you understand how your face center atoms form a octahedral void at the body center. Okay, so you have one atom here, and let's say you have one atom here. Okay, so these are the face atoms, right? Face center atoms. If you try to visualize it, my dear students, can you say that this is how your four atoms are present, and this is a atom above it, and this is a atom below it? You can just connect these four like this, and then you can say this and this. Doesn't it seem like something four atoms together? Four atoms touching each other. I told you the atoms do touch each other. One is above and the other is below. Yeah, so this is how you can find a body center, octahedral void in the body center of a FCC. Who makes the body center part as your octahedral void? The six face center atoms, and that actually is connected with six different atoms, and that is why it is known as the octahedral void. Okay, so the body center of FCC is octahedrally surrounded by six face centered atoms, these six face centered atoms. Therefore it is also a position of octahedral void. Okay, perfect. I hope you're clear with this, that why in a FCC your body center has a octahedral void. Now let's try to understand how your octahedral void is present at each midpoint of your edge. Okay, for that what you need to understand, you have a FCC structure, so definitely you have atoms here. You have atom here, you have atom here, you have a atom in the face center, you have atom here. So now you cannot visualize it because there are no six atoms present till now. For that, my dear students, you need to make other unit cells as well, those connected with unit cells. So let's try to connect them. Let's say this is connected like this, yeah, and this is connected like this, right? Yes, let's say this is something like this. Also you have a unit cell above at as well. Okay, so this is your unit cell. Okay, perfect. Now try to understand, since it is a FCC, so a center atom will definitely be present in this center as well. Okay, and a center atom will be present at this center of the face as well. Now try to look, how can a octahedral void be present at the edge center? See, these are the four atoms, and this is the atom above and this is the atom below. So can I say that again? I can see that I have four atoms present, and one atom is above and the other atom is below, and that is the reason this is my octahedral void again. This is my octahedral void again. This is how we saw for a single edge, and similarly for all the edges you get octahedral voids on each edge of the FCC lattice, right? Yes. So this is how you can imagine your octahedral voids present. I hope you're clear with this. So now, my dear students, you can pause the video. You want to write it, you can write it, and then we'll move forward. Okay. Perfect. Okay. So now the next question that comes to your mind should be that how many octahedral voids are actually present per unit FCC. So how will you be doing this particular type of question? My dear students, you will be finding actually how many your voids are present per unit cell. Okay, so now let's talk about the octahedral voids. Okay, octahedral voids in FCC, how will we find out? Okay, so now, my dear students, for FCC we know that one octahedral void is present in the center of the body. Since it is present in the center of the body of a unit cell, obviously it is not shared with any other unit cell, so the contribution would be 1. So the contribution is 1 plus, my dear students, you have 12 edges, and on each edge your atom is present, that is your octahedral void is present. Now let's see what is the contribution of a edge in a unit cell. Okay, so if I say that this is a edge, let's say that this is a edge. If we talk about this edge, my dear students, where all it is shared, one with the adjoining unit cell, Yes, the other, it is shared with the unit cell above it. I hope you're clear. And it is also shared with the unit cell adjoining unit cell as well, right? Yes. So it is shared between 4 different unit cells. So can I say that the contribution at edge is 1 by 4? So the contribution at edge is 1 by 4. So the number of octahedral voids would be number of atoms on the edge into the contribution, which is 1 by 4. So this would be 1 plus, how many edges do you have? You have 12 edges, right? Yes. And on each edge you have a octahedral void, so divided by 4, this would be 1 plus 3, which is equal to 4. So you have 4 octahedral voids present in a FCC, right? Yes. Can I ask you what is the rank of FCC? Rank of FCC is also equal to 4, right? Yes. Now, can you find the relation? Now you have to find a relation, and you have to say that number of octahedral voids in FCC is always equal to the rank. Similarly, my dear students, you can find another formula as well, that is number of octahedral voids in HCP is also equal to the rank. I'll make you understand this. I'll talk about the HCP as well, but for now you just need to remember these formulas. Okay, I hope you're clear with this. Perfect. Just a second. Okay, perfect. You can write it down and then we'll move forward. I hope you've written it. Now let's move forward. And now we'll be discussing about tetrahedral voids, because we have discussed everything about octahedral voids till now. Now, when we talk about tetrahedral voids, my dear students, tetrahedral void is a void that is made from 4 different atoms. It is a void which is made because of 4 different atoms. Okay, so it is a vacant space octahedrali that is surrounded by 4 different atoms. 4 atoms. It is not necessary that they are 4 different atoms, but 4 atoms is necessary. Okay. So now if we talk about how a tetrahedral void is formed, it is something like you have, let's say you have one atom, you have another atom, and you have another atom. So it will form a triangle, and one atom is present here. Okay, so this is how your tetrahedral void would look like. This is your tetrahedral void. A tetrahedral void is present something like this. Now let's try to make it even better. Let's say you have a spherical ball like this touching each other. You have 3 balls present in the same plane. There is a vacant space, and you put a atom above it as well. Okay, so this empty space sorry this empty space is your tetrahedral void. So tetrahedral void is made up of 4 atoms. The vacant space between these 4 is known as your tetrahedral void. Okay, yes, I hope you're clear with this. You can draw this down and then we'll move forward. Okay, so now again I told you that a tetrahedral void will be present only and only in the FCC and HCP. We are discussing about FCC now. Now we need to find out where the tetrahedral voids are actually present and how many tetrahedral voids are actually present. Okay, yes. So this is how we will be finding out the tetrahedral void. So for tetrahedral void, we need to understand a few things. Okay. So we know that we have a FCC structure. So let's say I have drawn a FCC structure. Okay. This is my FCC structure. So now for imagining a tetrahedral void, my dear students, you need to imagine a imaginary cube. Okay. So let me just draw a imaginary cube and then you'll understand what I want to make you understand. So this is your cube. So now how are you going to imagine? Just imagine, my dear students, you have one atom present here. You have one atom present here. You have one atom present here, and you have one atom present here. Your atoms are present on the only on these four corners. You have 8 corner positions in the cubic lattice, and only on these 4 your atoms are actually present. Okay. So now what you are supposed to do is try to connect these 3. If you connect these 3, you will see that one atom is present here, and this is how a tetrahedral void is made. So your tetrahedral void would be somewhere here. So can I say that this picture seems to be to me like this, and one atom is present here? This picture seems something like this, and a void would be present in the center of this imaginary cube, right? Yes. I hope you can see how I want to make you understand your tetrahedral void in this imaginary cube. Okay, this is the imaginary cube. Is this clear to you? Yes, I hope this is clear to you, because now we'll be using this particular part in this, the FCC. How are we going to imagine this now, my dear students? You have to imagine different mini cubes in this one bigger cube. Okay, so let me just draw a cube for you. I'll try to draw. Okay. Let's say this is the center. So something like this. No. This would be the center again. Then like this. Then like this. Then like this. You know my drawing. I'm sorry. I'll make it again. Okay. So this is the center. Okay. Finally, I'm successful drawing this imaginary cube. Okay. Yeah. Okay, perfect. So now, my dear students, what you have to imagine is I have made one imaginary cube, a mini cube, which is present in this bigger cube. Similarly, how many such mini cubes can I draw in this whole bigger cube? I can make one here, one at the back, one here, one at the back. So total 4 bottom and 4 above. So this single cube consists of 8 mini cubes. I hope you're clear. It exists of 8 mini cubes. Okay, one this side, the other would be there, then this side, then this side. So 4 below and 4 above. Okay, now if you see the atoms in a FCC, let's say this is actually the same unit cell. So the atoms are present. One atom is present here. Whoa. So your one atom is present here. So I have drawn this side. This is the face center and this is the face center. So your atom is present here. So I have drawn this and this. Then you have one atom present at the face center here. So one atom is present here. I hope you're clear. I am making this one. Okay. Then you have, my dear students, one atom present in this front face center. So let's say this is the front face center. Okay, so now, my dear students, if you can imagine, this looks something like the imaginary cube we drew, and in this imaginary cube's center, a tetrahedral void is made. A tetrahedral void is made. And how many such imaginary cubes can be present? Total 8. So in center of every imaginary mini cube, you will get one tetrahedral void. So total 8 tetrahedral voids can exist in a FCC lattice. I hope you're clear. I tried to show you how I have made the imaginary cube and how I have imagined the tetrahedral void. Okay, yes. 8 mini cubes. Center of each mini cube will give me one tetrahedral void. So total 8 tetrahedral voids. Okay, yes. So if you want to draw it, you can draw it. First, you want to draw the imaginary cube. Then you can draw this. And now we can say that it is a vacant space tetrahedrally surrounded by 4 atoms. And if the atoms are placed at the alternate corners, now you'll understand those lines, alternate corners on the opposite faces of the body center of the cube becomes the tetrahedral void. The body center of the smaller cube is tetrahedrally surrounded by 3 face centered atoms and 1 corner atom, and it is known as a tetrahedral void, right? Yes. You can pause the video, write it down, and then we'll move forward. Okay. I hope you've written it. Perfect, my dear students. Now we'll be writing the rank number of octahedral voids. Sorry, tetrahedral voids, right? Number of tetrahedral voids in FCC. So now we'll be talking about the number of tetrahedral voids in FCC. You have 8 mini cubes, and every mini cube's center you have one tetrahedral void. So total 8 tetrahedral voids are present, right? Yes. Can I ask you what is the rank of FCC? You will say the rank of FCC is, ma'am, 4. So can I say that the tetrahedral voids in FCC is actually equal to 2 times of rank? Right? Yes. So this is the formula that you need to remember, that tetrahedral void in FCC is always 2 times of the rank. Whatever the rank is, it is 2 times of the rank. So you have 4 as the rank of a FCC, you will have 8 tetrahedral voids. Similarly, tetrahedral voids in HCP is also equal to 2 into rank. Okay. This is the formula. I'll make you understand everything about it, but these are the few things which you need to keep in mind. Your tetrahedral voids are always more than the octahedral voids. Okay. Please write it down and then we'll move forward. I'll just have some water and then we'll move forward. Write it down. Okay, I hope you've written it. Now, my dear students, what are we going to discuss now? Now, you might have heard about layering. So now, my dear students, we'll be talking about different types of layering. Okay, we'll be discussing different types of layering. We'll be discussing one-dimensional layering, two-dimensional layering, and three-dimensional layering as well. So let's start. So first, we want to talk about voids. Voids are also of different types and different types of layering. So let's talk about voids in two-dimensional and 3 dimension. Okay, and 3 dimension. Okay, so now if you talk about 2 dimension and voids, my dear students, in 2 dimension we only consider a circle. So here we'll be considering circle as our atom, but if we talk about 3 dimension, we consider sphere as our atom. So here it will be a sphere. Okay, on the board obviously I'll have to draw it simply, but in reality it is something like this. Okay, so if we talk about the packing fractions, how are we going to find out that what is the packing fraction of one particular unit cell in 2 dimension? We'll always be talking about the area, okay, which will be pi r square. And if we talk about a sphere in 3 dimension, we'll always be talking about the volume, which is given by 4 by 3 pi r cube. Okay, so these are the few things which you need to keep in mind, so that we'll be very clear with the things how are we going to calculate the packing fractions. Okay, so now my dear students, when we talk about the voids, two dimension has two different types of voids. One are known as triangular void. Okay, the one is known as triangular void and the other is known as square planar void. Now let's try to understand this. What is a triangular void? When you have three circles present and you have a void in between, this void has a, if you see very closely, it has a triangle in between. So this is a triangular void. Okay. If you talk about a square planar void, my dear students, so how does a square planar void looks like? Let's say you have spheres like these. Okay, so these are present something like this, right? Yes. So if you have a closer look, you'll see that this is a square, kind of a square. So this is a, or you could say that these form a square, and in between there is a void. So this is your square planar void. Now let's try and talk about the coordination number of these voids. Okay, so now my dear students, the coordination number of the void is how much? You have one void which is made up of 3 atoms, so the coordination number is 3. If you talk about this void, how can you tell me that what is the coordination number of this void? The void is made of 4 different atoms, so the coordination number is 4. So the coordination number of square planar void is 4. So the coordination number of the void is 4. Okay, so this is how we find out the voids in the two-dimensional structures. Okay, I hope it's clear with you. Perfect, my dear students. Now let's talk about the 3 dimensions. Okay, so when we talk about the 3 dimension, we majorly classify the voids in 3 different types. The first is your octahedral void. The second is your tetrahedral void. And the third is your cubical void. These are the 3 different types of voids that are generally found in the 3-dimensional layering. Okay, yes, these are the voids which we will be studying. Now, if we talk about octahedral void, we have discussed about octahedral void. It is formed by 6 different atoms. So, it can be something like this. You have one atom here, you have one atom below. So this is a octahedral void, right? Yes. I'll try and let's discuss these types of voids individually, okay, on the next page. Perfect. Okay, you want to draw this down, please draw it, and then we'll move forward. I hope you've drawn it. Now, my dear students, we'll be discussing about 3-dimensional voids. Okay. In 3D, we'll be discussing about voids. One was your octahedral void. The other is your tetrahedral void. And then it is your cubical void. Okay. So now, if you talk about octahedral void, you know that octahedral void is made up of 4 different atoms, right? Yes, something like this, and then you have one atom above and the one atom below. If I want to draw it in a better way, I say that something like this, one atom is above and the one atom is below. So this is your octahedral void. Okay, I also made you understand that your octahedral void can also be present something like this. Right? Yes. What are you going to do? You will join these 3 and you will join these 3. So you see that you have one triangle like this and you have one triangle like this. So this is also your octahedral void if you are watching from here. So this is also your octahedral void. Now you don't understand this particular part, so let me make you understand. Let's say these 3 triangles are like this. Okay, so they are joining something like this. Now let's try to make these 3 in the opposite side. Okay, so you have 1 atom, 2 atom and 3 atom, right? So the other triangle is like this. Can you see a empty space in between this part? This is your octahedral void. This is your octahedral void. So this is how you can visualize your octahedral void in 3 dimension. Now let's talk about the tetrahedral void. Tetrahedral void we have discussed. The tetrahedral void is formed of 3 different atoms. And let's say you have one atom like this. This is above. So let me just draw it like this. Okay. You have 3 different atoms and this is not right. 3 different atoms like this, and then you have one atom here. So this is your what? Tetrahedral void. If we draw it in a better way, I'll say that these are connected together and your one atom is above this. So this is your tetrahedral void, right? Yes. So this is how you visualize a tetrahedral void. I hope you're clear with this. Perfect. Now let's talk about a cubical void. How does a cubical void is formed? Okay. So now for a cubical void, my dear students, you have atoms like this, and you have exactly like same, I am drawing it with a different color so you'll get it, exactly same atoms above them. So if you try to draw them, you will have 4 atoms of blue, and then let me draw 4 atoms of green. So if I join them, I'll get something like this. And these together form a cube. These together form a cube, and the space between them is your cubical void. This is what is known as a cubical void. Okay, so this is also your cubical void. So in 3 dimension, you come across these 3 different types of voids. Okay, yes. So you need to have a clear picture of how a void is to be located, because you will be asked a lot of questions based on these geometries. Okay, yes. So you need to write it down, draw them, understand them, and then we'll move forward. I hope you are clear with this. Okay. Yes, you're clear with this. Now let's move forward, my dear students. Perfect. Now the thing which we have discussed in 2 dimension, now we'll try to calculate the packing fraction. I'll make you understand how to calculate the packing fraction. If you'll understand in 2 dimension as well, then you can find out packing fraction in any question, and many a times question is asked to calculate the packing fraction of different types of layerings. Okay. So now, my dear students, let's talk about the packing fraction in 2 dimension. Packing fraction in 2 dimension. Okay, so if we talk about packing fraction in 2 dimension, you have how many types? 2 different types of layerings. Okay, so let's try to understand first. Let's try to understand the layering, and then we'll try to understand the packing fractions as well. Okay, so let's try and let's start a topic which is known as layering. Now layering is actually that how your unit cells are formed. Okay, till now we studied about a unit cell, but now we'll understand how we imagine a unit cell. Okay, what is a unit cell? A unit that is repeating itself again and again, and you're getting your crystal system. Okay, so let's talk about layering. The first is your one-dimensional layering. One-dimensional layering. So in one-dimensional layering, my dear students, you'll obviously have one axis. I hope you're clear with this. Let's say you have one atom here. So you'll have one atom here, 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 and so on. And this would be the one-dimensional layering. So if you have to find out the coordination number of one atom, you'll always take an atom which has the same atmosphere. So this atom has same atmosphere symmetry, and it is directly connected to two different atoms. What is coordination number? The nearest neighbors which are direct in contact. So only two. So we'll say the coordination number is 2. So in one dimension, the coordination number of an atom is always 2. Okay. Yes. I hope you're clear with this. You can write it down. Now let's talk about the two-dimensional layering. So if you talk about two-dimensional layering, now two-dimensional layering can be of two different types. It could be, my dear students, now we'll be discussing about the two-dimensional layering. It could be your square packing, and also it could be your hexagonal packing. Okay, so now we'll be understanding these types. So now, if you talk about the square packing, how your square packing actually exists. You have atoms like this. Just a second. Huh? So you have atoms like this. No. Okay. Yes. I think this will take a lot of time. So this is how your layering starts in square packing. Okay. So similarly, you draw layers like this. I'll make on my own because it is taking a lot of time. Okay. Yeah. Let me just make one more layer. So this is how your square packing looks like. Okay, your square packing is one layer on the above, then. Let's say this is A type of layering. Okay, so this is your A type of layering, and this is known as your square packing. Okay, and we are talking about two dimensions. So this is how your square packing looks like. Okay, perfect. So now what happens, my dear students, is let's try to see that which type of voids are present here. Okay, so let me write it as voids present here. Which type of voids are present here, my dear students? Which type of layers are present? Just tell me. Can I say that you can think of this type of void? So ma'am, you have what? Square planar voids present here, right? Or you could say square voids. Yes. Now, can I talk to you about the coordination number of the void? Ma'am, the coordination number of void is, it is connected by 4 different atoms, so the coordination number is 4. Now let's try and understand. Now let's try and understand, my dear students, about one particular atom. In this packing, the coordination number of the atom. Now I'm not talking about the voids. Now I'm talking about the coordination number of the atom. So the coordination number of atom here would be, let's talk about this particular atom. So this atom is directly connected to 1, 2, 3 and 4. 4 atoms. So the coordination number of the atom is also 4 here. Right? Yes. So this is how we can see the first type of packing. Now let's talk about the hexagonal packing. Now if we talk about the hexagonal packing here, my dear students, I'll have to draw this again. You will have one atom. You will have another atom. You will have another atom, then you will have another atom. Okay, similarly you will have atoms like this. Need to draw it in a bigger size. I am trying to draw best I can. Okay, so atom would be present something like this, something like this. Yeah, then you have atoms like this. Okay, so now here, my dear students, if this was A layer, this is exactly same, this is exactly same. So I can say that this is AAA type in 2 dimension. Now let's talk about the hexagon type. Why did we call it as square packing? Because if you connect any 4 atoms, you can form a square, and that is the reason it was a square square packing. Now we are going to talk about the hexagonal packing. Why do we call it as a hexagonal packing, my dear students? Because if you see, if you connect the centers of all the atoms, you can find out a hexagon here. So the first and the most important thing, why do we call it as a hexagonal packing, is this. Okay, because it forms a hexagon. Perfect. First thing is clear. Now the next thing is, which type of voids are present here? So can you tell me the type of voids present here? Just try to see. It is a triangular void. Yes. So here, my dear students, your triangular voids are present. Triangular voids are present, right? Yes, triangular voids are present. What else? Next we have to find out the coordination number of void. The coordination number of void would be, how many atoms are forming this void? 3 atoms, so the coordination number would be 3. Now let's try and understand what is the coordination number of an atom. So the coordination number of atom in this layering would be, let's talk about this atom. It is connected by 1, 2, 3, 4, 5 and 6. 6 different atoms. So the coordination number of this atom would be 6. Right? Yes. And what is the type of layering? If this is A, then this is B, and this is again a layer A, because you see that the layer or A's are same and the B would be same. So this is a AB type of layering. Okay, in 2 dimension. So these are the different types of layerings present in the 2-dimensional part. Okay, yes, this is something very important. Try to understand this. Please write it down and then we'll move forward. I hope you've written it. Okay, perfect. Now the next thing which we will be doing is calculating the packing efficiency. Now we will be calculating the packing efficiency. Okay, so the first is in square close packing. So we are calculating this packing efficiency in 2 dimension. Okay, in 2 dimension we are packing this. We are actually calculating this. Okay, so now try to understand this. I'll have to draw AA type. So this would be AA type, since the layers are exactly same. Right? Yes. So how are we going to calculate the packing efficiency? I hope all of you remember that for packing efficiency, since now it is 2 dimension, we'll have to talk about in terms of area, not in terms of volume, because in 2 dimension you only have area. So area of atoms upon area of unit cell. So first we have to find out a unit cell which is repeating itself all over again. Can I say that this is a unit cell and it is repeating all over again? So the unit cell is a square. Okay, and the edge length is, let's say, A. Okay, the first thing that I have found out is this. And can I find the relation between the radius of the circle and the edge length A? I can say that this is radius R, this is radius R, and this is edge length A. So I can say that A is equal to 2R. This is the first thing that I have found out. Okay, now I need to find out the rank, that is how many atoms are actually present in a unit cell. Okay, so number of atoms will be, let's see what is the contribution of one atom in a unit cell. This is 1/4 part of the sphere which is present at the corner of the cell, right? Yes, so can I say that the contribution of atom is 1/4? The contribution of one atom is 1/4. So what will be the total number of atoms present? Total number of atoms would be present. Contribution is 1/4, and how many atoms are actually present? 1, 2, 3 and 4. So I can say that 4. So the total number of atoms that are present is 1, right? Yes. What is the total area of square? It is A square, because it is a square. So now let's try to calculate the packing fraction. Easy. Your packing fraction is actually equal to total area of atoms. How many atoms do you have? 1. And what is the area of one atom? Pi r square divided by A square, the area of your unit cell. Okay, I know the relation of A and R, so I'll use it in this. So the packing efficiency will come out to be pi r square upon A is equal to 2r, right? Yeah. So 2r whole square. So this would be pi r square upon 4r square. Let's cancel r square by r square. So pi by 4 is the packing fraction. Actually, we are calculating packing fraction, not packing efficiency. If we had to calculate the efficiency, we had to multiply it by 100. Okay. So this is the packing fraction. So write it down, packing fraction. Okay, perfect. Or packing fraction. Right? Yes. So this is the packing fraction. What would be the void fraction? Void fraction would be 1 minus packing fraction, which is 1 minus pi by 4. Right? Yes. So this is how you will calculate this. This would be equal to 3 pi by 4. This is actually how we will be calculating the packing fractions. I hope you are clear with this. Okay? Yes. Perfect, my dear students. You can just pause the video, write it down, and then we'll move forward. I hope you've written it down. Perfect. You can write this down as well. There is some error with it. This is 3.14. Your fraction would come out to be this 4 minus this is 3 by 4 pi. This is 1 minus the packing fraction, right? 1 minus the packing fraction. This would be 1 minus pi by 4. And this would come out to be 1 minus 0. That is 314, right? So 0.3 would be 3 and 1, right? 0.314. So that would be 32. 0.9 something, right? Yeah. So this is how you will calculate. Just calculate the full value here. Okay. Yeah, perfect. So now, my dear students, your homework is you have to calculate the packing fraction of hexagonal packing. Okay. So now you will have to calculate the packing fraction of the hexagonal packing. This is your homework. Okay. Yes, perfect. Try to do this. You'll have to draw that. Then you'll have to find a unit cell. And the unit cell which is repeating, I told you the hexagon would be the unit cell. So try to calculate the packing fraction. I'll make you understand how to calculate it further. Okay. Yes. We'll discuss the three-dimensional layering in the next class. We'll be discussing the three-dimensional layering in the next class. Okay. Yes, perfect, my dear students. Now let's move forward. Now let's try and do some questions which will actually help us to have a grip on the concepts which we discussed today. Okay, and three-dimensional layering we'll discuss tomorrow. So now the question says that in which of the following pairs of structure tetrahedral as well as octahedral holes are found? Where are they found? They're not found in the primitive and they're not found in the body centered crystal systems, else they are present, right? Yes. So it is not present in BCC, not present in simple cubic, HCP and CCP, yes, not present in BCC. You know that CCP is your FCC. So yeah, option 3 will be your correct answer. Okay, perfect. Now let's move forward. Next is the number of octahedral voids in the BCC structure is. You'll have to tell how many number of octahedral voids are present in BCC. Now, my dear students, I told you that octahedral voids and tetrahedral voids are not present in BCC. So, octahedral voids and tetrahedral voids are not present in BCC. So, the answer would be 0. So, option A will be your correct answer. Perfect. Yes. Amazing, my dear students. You can write it down as well. You can write this down as well. Now let's try to do this question. The question says that you have element B who forms CCP. So you have element B who forms CCP and you have element A occupies half of the octahedral voids. So it occupies half of the octahedral voids. Okay. While oxygen atoms occupy all the tetrahedral voids, it occupies all the tetrahedral voids. The structure of the bimetallic oxide is. Okay. So you have to tell this element B forms CCP. Now since, my dear students, it is forming BCC, I know that CCP, I know that rank is equal to 4. If rank is 4, can I say that tetrahedral voids would be 2 into rank? So that is 2 into 4, which is equal to 8. And I know that octahedral voids is always equal to the rank. So octahedral voids are 4. Now it says that B forms CCP and it occupies all the space. So this would be 4. If you talk about A is half of the octahedral void. So you have octahedral voids 4. And oxygen occupies all the tetrahedral voids. So this would be 8. So now let's try to find out. This would be something like this. So let's take LCM 2 on all the parts. So this would be B2, A and O4, right? So A, B2, O4 or B2, A, B2, O4. Yes, option B will be your correct answer. So this is how you have to solve this question. When you find the easiest portion, this means that 1:1/2:2. So you'll have to take the LCM. So this would be 2. This would be again 1, sorry. And this would be 4. So this is how you find out the correct formula, that is AB2O4. Okay, and these types of questions are asked a lot, so you need to have a best grip on this particular part. Okay, perfect. Please write it down and then we'll move forward. Now let's try to do this question. What does this question say? The correct statement for cubic close packed CCP three-dimensional structure. So basically you have to tell the correct statement for FCC. Okay, the first says that the number of nearest neighbors in an atom present in the topmost layer is 12. My dear students, we will not be able to do this question right now because we haven't studied the layering till now. Okay, so we'll do this question in the next class. We cannot do this question right now because we need to understand the layering of the 3 dimension. Only then we'll be able to solve this question. So we'll solve this question in the next class. Okay, with this, let's end our session today. I hope you have understood every part of it. I hope you were able to solve the questions. I hope you were able to imagine what I wanted you to imagine, right? Yes. So my dear students, you need to have a better understanding of everything in solid state. You need a good imagination and you need a lot of practice. So keep solving questions, keep understanding concepts, and definitely go through the NCERT for this particular part because the layering is explained exceptionally good in the NCERT. Okay, yes, we'll study the 3-dimensional layering in the next class. We'll meet in the next class. Till then, keep studying. Thank you so much. All the very best.